So, yeah, so remember that functions at their very basic form are just ways to define a pattern, a certain thing that's happening, a rule that you can depend upon to find the next piece in the pattern, right? So we're going to start there. We're going to look at this as a pattern, and then we're going to try to graph it and then see if we can define it with a rule. So there's like kind of 3 steps in there. It's like, can we identify the pattern? What's happening? Can we extend the pattern? Like, can we add to the pattern? And then can we define the pattern? Can we make the pattern useful for any situation? Okay? So that's what you want to do here. Get as far in those 3 steps as you can. Okay? And then we will go over that. I'll give you some time to do that if you haven't yet. Hopefully you recognize some things. All right, so let's talk about this warm-up, and then that'll help us catapult into our lesson today. So, like I said, the functions are patterns, right? And the function that you create with a formula or an equation is just a definition of a pattern or a sequence or a rule that will allow you to find any part of that rule in that sequence, right? So the first step is to identify the pattern, like what is happening every time to get you from one thing to the next thing. So when we look at this, we say, okay, well, x is going up by 1, right? But then y has something else to it, right? We go from 3 to 5 to 7, right? So there's some consistency here that must be getting you from one number to the next, and we realize that is what? We are adding 2 every time, right? So the pattern is plus 2 each term, right? And each of these is a term. That's a term, that's a term, that's a term. So to get from one term to the next, we add 2, right? So that's step 1. We've identified the pattern. Step 2 is, can we extend the pattern? Can we apply the thing that we found? So then we try to fill in missing pieces. So we say, okay, well, if this goes 3, 5, 7, and I want to go again, I would say the next number is 9, and then the next number is 11. Okay, so now we've extended the pattern. We are able to continue the pattern that we've identified. Then the next step is, can I define the pattern? Because if I can define the pattern, I can find it for any piece, right? And in other words, like, for example, what if I wanted the 20th spot in this pattern? And I didn't want to have to add 16 more times, right? I just wanted something that I could find the 20th term just like that, right? That's where you need to define the pattern. That's where you need a formula or an equation that you can plug into and find any. You can find the 20th, you can find the 100th, you can find the millionth, right? So that in order to do that, in order to define the pattern, that's where you need to take a step back and think about, what type of pattern do I have? And because every different type, linear, quadratic, exponential, whatever, logarithmic, they all have different forms, right? So in order to, we might already know what this one is, but in order to find what type of pattern you have, you can graph it and you can look at the picture to help you say, oh, it's one of those. It's one of those types, right? So you would graph this thing. You would take, if you didn't know, you would take your points, your x's and your y's, and you'd add them to a graph, right? And you would say, okay, well, my first point was 0, 3. My second one was 1, 5, and then I had 2, 7, and then I had 3, 9, and then I had 4, 11. And then you would say, okay, I see it now. Maybe you had already, but if you hadn't, here's your process, right? And you say, oh, that is in the shape of a what? A line, right? So I know the type of pattern that I have is a linear pattern. Why is that important? Well, in our process of trying to define the pattern, we've now discovered the form. Because we know linear patterns, we know what form they come in. What form do linear patterns come in? What's that basic form that we always use for lines? Y equals mx plus b. So now we're working in a zone where we can actually write a rule and write a definition for the pattern, okay? So I need to find the pieces of that, the m and the b, right? So I ask myself, okay, what's the m and what's the b? And this is where we get into our knowledge of linear functions, where we can find that different ways. Some people might say, well, I know your slope, your m is what it changes by every time. And they say, well, that means my m is 2, right? And they would be right. And then other people might say, well, I remember it from the graph where it's the rise over run, and this goes up 2 over 1, and 2 over 1 is 2. And they would be right too, right? So you use your knowledge of that type of pattern. I also know that the b happens when? It's our starting point. It's when our x is 0. It's our y-intercept, right? So that's our other piece. We found our pieces. We plug in our pieces, and we have our definition, our defined pattern of y equals 2x plus 3. Why is that a definition? Why is that the pattern defined? Because that allows us to find any piece of the pattern, whichever one we want. For instance, we wanted to find the 20th spot, right? Well, if x is 20, we can now find y by just plugging in. We can say, okay, well, y equals 2 times 20 plus 3, right? We just plug in the 20, it pops out our y, which was 2 times 20 is 40, 40 plus 3 is 43. So there you go. We now know that the 20th term in this pattern would have been 43 if we added 2 a zillion times, or 18 times, or whatever, how many times we needed to from our start, okay? We don't have to do it. We can just plug in because we've defined this with a rule, okay? That's the process for any function that you just looking at a pattern and you don't even know what type of pattern it is. That's the process. Identify, extend, defined. Okay. Now that takes us to today's focus, which is a different type of pattern. So pretend we're starting from the same point. All we know is the pattern, right? Nobody's even told us what type it is yet. So the first thing we do is identify it. This goes from 3 to 6, and then 6 to 12, and then 12 to 24. So I think, what is happening every time? It's multiplying by 2. So multiply by 2 each term. Okay, we've identified. Now we would like to expand or extend. So 24, what would be the next term? 48. And then we come to the same point where we're like, all right, well, now I kind of want to know any point in this pattern. For instance, maybe the 20th. And I don't want to have to multiply by 2 18 times or 16 more times, right? So I'd rather just have a rule and a definition for this pattern. But I need to remember what type of pattern it is, so I'm going to see what it looks like on a graph. And maybe that'll help me remember, okay? So I plot my points. 0, 3, 1, 6, 2, 12, 3, 24, 4, 48. And I notice right away I don't have a line. I don't have a line at all. I have this curve. And in fact, it gets faster and faster as it goes, right? And hopefully, I remember by looking at this picture what type of pattern this is. This is a what type of pattern? Now, quadratic would be a U shape. Square root would be like that. Exponential. Yep. And exponential growth is something that consistently goes up. It's not like it goes down and then it goes up. It goes up, like this would extend out like this, right? It goes up, 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 and keeps going up, 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 up. Doesn't change direction, and it gets faster and faster as it goes. So it's exponential. Okay?
Can it be a square root, though? Because square root you said is just...
Square root would go like this, right?
But can it be modified to become that graph?
Well, you would change, that would be changing the function. So this is exponential. And then I would, just like with linear, I would say to myself, okay, since I know it's exponential, I go back to my knowledge of exponential functions. Now maybe this is where we need a little refresh, because this is the whole idea of today, is we're going to review exponential functions, okay? So if at this point you're like, well, I don't know the y equals mx plus b for this one, that's okay. That's why we're doing this. That's why we're reviewing it. But there is a form that you can use to plug in and define this pattern too. Does anybody remember it? Good. Okay, so let's take what you just said, and let's just say we don't even know the rule, but what's happening here? Well, where did this thing begin? Like, what is this first point when x was 0? 3. And then how did we get to the next point? We multiplied by 2. And then how did we get to the point after that? Multiplied by 2 times. And then we multiplied by 2 3 times. Multiplied by 2 4 times. So it's 2 to the power of x. Well, you forgot the starting point, but you were close. You were close. So that is it. Like, so you can kind of think your way through it too, right? It's your starting point, and then times your multiplier, and then how many times you're going to multiply, right? 1 time, 2 times, 3 times, right? So, what's that?
What's the 2 minutes?
3 times 2 to the x. All right, so let's take a step back and let's write this. A moment ago I said, hey, what's the y equals mx plus b for exponential functions? Well, this is it. It's y equals ab to the x, okay? This is your mx plus b. Remember before, we wanted to plug in for m and plug in for b. Well, now it's a and it's b, right? Once you find those two pieces and you plug them in, you have written the formula for this, okay? So, well, we need to know what a and b are then, what they stand for. Now, look at our example. What was our a? Our a was 3. What was that, though? It's our starting point and our y-intercept. And our y-intercept happens when? Yep. So when x equals 0. Now, interesting. So whenever x is 0, our y will just be a. Just the a value. Why does that happen? Well, think about it.
Well, it's anything to the power of 0 equals 1.
Exactly, right?
You'll just end up
So if x is 0, right? Yeah. That means this is 0, and then b to the 0 is 1. So it's y equals a times 1, or y equals a, and that's your y, right? So that's exactly why it has to be our y-intercept. Okay, so if that's our a, then our b
is the pattern.
the pattern, but in this case, the pattern is done by multiplying. So it's our multiplier. Yeah, it's our multiplier. It's what we multiply by every time. Okay? And then if we want to talk about our y and our y is, of course, our output, our final amount. And our x, it's not just our input, it's also the number of times we multiply. Right? If I raise it to the third power, that's because I'm multiplying by 2, 3 times. Okay? All right, so we have these exponential functions. We need to be able to recognize them in 4 different ways: as a pattern, in a table, on a graph, and in a function. So we're going to talk about those ways now. Okay? All right, so we have this pattern. Now, when you just start with a pattern, you have to somehow get this into an input-output situation, an x and a y, so we can start to turn it into a function, right? And it's giving you the outputs. Like, these are your outputs. Right? These are the results. So the question is, what are our inputs? What are the inputs if these are our outputs?
It's 1, 2.
Exactly. So it's 1, 2, 3, 4. Why? Because if these are our terms, these are our term numbers. It's like your place in the pattern, right? So our x is the term number, and our y is the term itself. Okay? Now, with this new framework of thinking of it as x's and y's, we can now move to a table and start getting closer to a rule, a function, something that we can define. Okay? So we put in what we know. Well, I know 1, 2, 3, and 4, right? That's 10, 20, 40, 80. But I have a missing piece. I have that x of 0. What would the y be for that? 5. Has to be 5. Right, exactly. If you're multiplying by 2 to go this way, right? Well, this is going backwards, so we would divide by 2, right? Which would give us 5 here. And now we know that critical y-intercept. We're going to need that, right? So it's always important to get that in your table. Okay. So we throw it onto a graph. We got to be able to graph it. We got 0, 5, 1, 10, 2, 20, 3, 40, 4, 80. All right. Now, this is an important piece here. Let's make sure we understand this. Ready? Okay, I'll ask you a question. Should my graph look like, and wait for me to finish, that? Why not?
The bottom should be. It's never gonna touch x.
Because we started on 0.
Very good. Why?
You start at 0, so it shouldn't extend out.
Yeah, it's like there's like x and then.
I agree with you that this is what it will look like. But I want someone to tell me why it has to be that way.
Oh, because
It's not gonna go negative.
you can't
Why not?
multiply in a negative way.
You're right. Go ahead, Hannah.
When both terms are positive and you multiply or dividing, the output will always be positive.
Good. Yeah. Even if it's like super, 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 super small, right? Yeah, it's still not negative, right? Very common mistake that I see on a test or a quiz is people just keep going down, right? Think about it this way. If we went, how do we go backwards again? Instead of multiplying, we? Okay, so I divided by 2 and I got 5. Now divide by 2 again. Then divide by 2 again. Divide by 2, divide by 2, divide by 2, divide by... Are we ever going to get to 0? No. Tiny. It's going to be almost... You can't even tell the difference between 8 and 0 because it's so small on a graph, but you'll never cross. Good. Okay. Last piece. Now we throw in our pieces into the function. Y equals AB to the x. I need to know my A and my B. What's my starting point? 5. What's my multiplier? 2. So it's as simple as that. Y equals 5 times 2 to the x. Right? Now I could find that for 100 if I wanted to. Okay, I've defined it. Now I can plug in, find whatever I want. Okay, now there's a couple other pieces here. here's the thing. This ain't the only situation. You can grow, but you can also decay, right? If you think about growth, a good example is like how a disease spreads or something. It grows exponentially. COVID is a great example, right? It just kept getting faster and faster because more people would get it and give it to more people, and then it just multiplies. The same can be true for decay, for a decrease. Decreases aren't always linear either, right? If you have a virus in you and you take medicine, and let's say that virus is at 100 in you, and you take the medicine, it knocks it to 50, right? Right away you feel a lot better, and then the next thing it does is knock it to 25, and then to 12.5, and little bit. So decay decreases really fast and then slows down, whereas growth grows slowly and then faster, okay? So we need a way to define that too, okay? And that comes up. So let's talk about it. Talk about growth and decay. Now, our example above was what? Growth or decay? Growth. And here it is again, right? So, why did it grow? Because the multiplier was what? Well, greater than 1, yeah. So it was greater than 1. When you multiply 5 by 2, is it going to go up? Yeah. If you multiplied 5 by 5, would it go up?
Yeah.
If you multiplied 5 by 1.5, would it go up?
Yes.
Yeah. What about 1.1?
Yes.
What about 1.0001?
Yes.
Yes. Because even though it would be the tiniest little bit, it's still going up, right? What if you multiplied it by 1?
Stay.
Nothing would happen, right? Multiplying by 1 gives you itself.
Yeah, it'll stay.
What if you multiplied by 0.9?
That will decay.
Now it goes down, right? So that's why it's our breaking point. It's about what happens when you multiply, right? So growth, our B is what? Greater than 1, right? That makes it go up. Question?
What if the b is negative?
Good question. We'll get there. I'm glad you asked. Okay, so you brought up an interesting point. When we say decay, the typical response from students is like, oh, well, if b is greater than 1, then that means for growth, then that means for decay, it must be when b is less than 1, right? So all I got to say is b is less than 1. But you bring up a good point, because what if it's negative? So let's go with an example here. It is less than 1. So what I'm saying is that might not be enough. Let's look at this. Let's say I have y equals 10 times negative 2 to the x. That's a b that's negative, right? Okay. And I'll make a table. X, y.
Wait.
0, 1, 2, 3, 4.
Wait, it'll be inconsistent.
It will be very inconsistent. Let's see what happens. Well, we know 0 will be our a value. Now multiply it by negative 2.
It'll be 2.
Negative 20. Now multiply that by negative 2.
It'll be
Positive 40. Now multiply that by negative 2. Negative 80. Now multiply that by negative 2. 160. How about we graph this? Let's see. It'll be like, here, hold on. That, then down here, then up here, then down here, then down there, and it'll be like this. Oh, come on.
There's so much algebra and physics that hurts.
So is that exponential growth or decay?
No. Yeah.
So what's our rule here? Not only is it less than 1, it has to be greater than 0. Okay? That will make it go down. That's decay. Between 0 and 1. Pick a number between 0 and 1, and it'll multiply by that, and it'll go down. Okay? Let's look at some examples here. Here we go. 5 times 4 to the x. Is that growth or decay, and how do you know?
That is
growth, there's two ways you could know.
It goes up. It's a positive number. It's a number greater than 1.
It's a greater than 1, so it fits our definition. B is greater than 1. How else could you know? What if you forget? You're on a test, you're like, I forget the B thing.
If it's not a fraction.
If it's not a fraction or a decimal, or you can just think to yourself, what would happen if I multiplied 5 by 4? It would go up. Question.
It would still be a fraction, just
Could be like,
larger.
that's a good point. Yeah, it could be 3 halves would make you go up. Yeah. So 5 times 4 is 20. Does that go up? Yeah, so it's growth. So you can always just test it, right? So if you forget the rules, just think about it, okay? Now, f of 3, remember, that just is asking you to plug in your x. So this is 5 times 4 to the third, which is 320. Okay. All right, and then this one, growth or decay? Decay, because b is between 0 and 1. You forget the rule, you just say to yourself, well, what would happen if I multiplied 180 by 0.8? Let me test it in my calculator. Oh, it went down. That's decay, right? Now, if you did to the 4, that's 180 times 0.8 to the 4, which would be 73.7-ish. That. Now, there's a way you could sense check both of these. We said this was growth. Did it grow? We said that was decay. Did it go down? Yes. So you could always sense check your answers. What's that?
How did we get 320?
I don't know. Was it not right? Is 320 not right? Did anybody check my work?
Yeah, it's 64.
4 to the third times 5.
I misread it.
That's okay. All right. Last piece. Ready? Now, we need to be able to graph and we need to be able to write functions. You pretty much have been given all the information for this. This page is more about here's your strategy, okay? And your strategy for both of these situations, to graph or to write exponential functions, is make a x, y table. In either case, because both of these things are the same thing, just forwards and backwards, right? In this case, if I'm graphing and I make an xy table, well, I'm going to fill in the table by doing some math. Okay? I could either plug in each of these into my function to pump out my y's, or, and this is where I give you the trick and the advice, what number is super easy right now? 0, because that's just my what value? My a value. And what's my multiplier? 3. So what would this next one be? 2 times 3, which is 6. 6 times 3 is, now what if I wanted to go backwards? 2/3. 2/9. Right? And I just filled it in the table. I didn't have to plug anything in. Okay? Well, the fractions we kind of want to just know to estimate, right? So I have 0, 2, 1, 6, 2, 18, and then backwards I got 2/3, about there, 2/9, about there. It just kind of gives me a little reference point. So now I go like this, and I have graphed. Okay? So you can always plug in, but you don't necessarily have to if you know how exponential functions work. If you know your a and b and what they do. Okay? And now, same thing for that next one. I'll leave that for you. Now, if I'm writing, again, x, y table, this time you pull points right from the graph. So you look and you say, well, there's my starting point. There's the next point. There's the next point. Let me pull them out and see what they look like. So that's 0, 4, 1, 12, 2, 36. Okay? Now it's on you to write the exponential function. So you need to find your a, you need to find your b. Right? We know that y equals ab to the x. So our a is our starting point, which is 4. Our b is our multiplier, 4 to 12, 12 to 36. 3. So y equals 4 times 3 to the x, and you're done. Right? So the table kind of connects the dots both ways, whether you're graphing or writing. Now, one thing with decay, this is the last piece, and then I'll give you your homework. Let's say we use that same process right here. We make our table. Here's a point. There's a point. There's a point. Let's see. So that's 0, 1, 2. And I got 36, 12, and 4. Okay. Not as straightforward, right? Because if I'm trying to find y equals ab to the x, well, my a, I can find. That's when x is 0. What's that? 36. But my b is my multiplier. And I multiply something by 36 and I get 12.
It's a fraction.
It's got to be a fraction because it's going down. What is it?
I was going to say you divide the first number by the second number and then put the 1 over your first, the final number.
So some people see this and say, oh, you just multiply by 1/3. Some people are not great with multiplying fractions, and they have to be able to be given a way to calculate this. So you take, if you can't find your b, and this works for the last problem too, by the way. This will work for any problem. Take any number and divide the previous number. So let's say I took 4, and then I divided by the previous number, which is 12. That reduces, right, to 1/3, which means 12 times 1/3 is 4. That is your b. So 1/3. So this turns out to be y equals 36 times 1/3 to the x. And I mean it, like it would work here too. Remember I said take any number and divide by the previous number. What's 36 divided by 12? 3. So it gives you your b in any situation. Okay? All right, so let me give you your homework.